don't have permission, which is not good. Okay, welcome everybody to this seminar, special seminar, because we have a very, very special guest. It's a pleasure to introduce you, Juna Kollmeier. Most of you already know her, but in case not, she's one of the big shots in cosmology. After having been graduated, I think, bachelor in Caltech, MSc and PhD at Ohio, correct me if I'm wrong, and then trips to Princeton and faculty at Carnegie, where she was, I think, director of theoretical astrophysics, and then swapped to a very interesting place called CETA in Canada, the National Institute for Theoretical Astrophysics of Canada, where she is director since about 1 year. And she has a whole lot of work to do. Sometimes more on astrosociology and astropsychology than in astrophysics, but that's what we all do. And so we have the great honor to have Juna with us in Belgium for a whole month, because she's actually the 2022 Solvay Chair in Physics, which is a great honor, a prestigious appointment. And so we are honored that she is here for a couple of weeks, returning to us after she was here just pre-pandemic and now returned, and here until third week of July, in fact, being with us for the full conference that we are heading for mid-July. But today she's gonna give some kind of pre-flash on the Sloan Digital Sky. And there are 3 lectures that she's delivering, Solvay lectures, next week at ULB in Brussels. So you're all invited, of course. But let me give the floor to Juna and thank her in advance for her contributions to astrophysics and cosmology in this country. Juna, please.
Thank you, Connie. It is a pleasure to be here. It's always nice to visit Belgium. And as Connie said, the last time I was here was in 2019, right before the world completely changed for all of us, I think. So it's really pleasure to be back, and I want to thank Connie, who is an inspiration to me personally, but I know to many of you as well, and also appreciate that Connie took time out of her schedule because she's busy collecting awards all over the world, and so it's a very exciting time and place. I want to, being here at KU Leuven in particular really strikes me. You know, you have this through line all the way from Lemaitre to today, and that through line really is to embrace the dynamic universe. So of course, Lemaitre famously appreciated that the universe could be non-static. And of course, today, with all of your work in astroseismology, appreciating the lack of, or the dynamism within stars, I think it's very appropriate that this dynamism is happening here at KU Leuven, and it's really exciting to connect with that history. Now, when I was here in 2019, I showed you guys this slide. These were our robots that had been being tested in Switzerland. And you can see, of course, what we were doing in SDSS-V is we're roboticizing the original hardware. I'll talk more about what we were doing. But this was from my 2019 talk, where I showed you how our robots were moving in Switzerland. This, by that point, was already an old movie. And we were ready to commission at Las Campanas mid-2020, as soon as SDSS-4 was over. That was the plan. And of course, we all know that that plan could not come to be. And so this is partly a bit of a talk from the coal mine, because we have been really, really hard at work within SDSS for the past 2 years, trying to make sure that we could actually build this hardware getting it to the site and getting it working. Too long, didn't read. Just for those of you who are kind of feeling sleepy after those delicious sandwiches we had, SDSS-V is commissioned and on Sky in New Mexico. We are shipping Unit 2 to Chile on Monday. So I want to go through some of that struggle, and particularly for some of the students in the audience online and here, many times in your career you will face different types of struggle, and how we handle those moments are the key to figuring out the secrets of the universe. SDSS has a tradition of theory-driven experiments. As Connie mentioned, I began the theory program at the Carnegie Observatories, and I'm now the director of the Canadian Institute for Theoretical Astrophysics. And I want to just emphasize how important theory is in guiding experiments like SDSS, like these large surveys. And I know that's something that is very central to how you guys roll here in Leuven, but it is so important to connect data to theory. This is, of course, Jim Gunn, who was the originator of the idea in SDSS-1 and 2, and his idea was to get 1 million redshifts for cosmology. In SDSS-3, Daniel Eisenstein, the director there, they did these 4 programs, in particular building the apogee spectrograph, which probed stars in the Milky Way, and then SDSS-4, which completed a year ago, which was filling in the gap in the cosmological redshift space, and also building another unit to go south, another unit of the apogee spectrograph to go south, and also brought SDSS into the sort of IFU era. And so in that, I am continuing this tradition and also changing up the tradition, as you can observe. What is SDSS? So SDSS has these 4 components. So it's a science survey. It's a science survey with 3 mapper programs. It's an observing facility, so we've got telescopes and instruments and software. It's a consortium of partner institutions, and it's a collaboration of people. So SDSS has these many different entities associated with it, and each one of these is extremely important. And in doing a project of the scale of SDSS, it's incredibly important to focus on every one of those things. And in particular, what we're doing in SDSS-V is all sky time domain real spectroscopy. And I think that dynamic aspect is key. So SDSS is a global consortium. There are over 70 institutions, including KU Leuven, spanning 5 continents. In fact, Leuven was one of the first members because Connie Earts was part of the steering committee for SDSS and part of shaping the program that we have today. How does, when you're on an airplane and they say, you have your choice in airlines, thank you for flying blah, blah, blah airline. You have your choice in spectroscopic surveys, thank you for selecting SDSS-V. It's an incredibly rich time in spectroscopy. And many, many different surveys have existed or completed. In particular, as you guys all know, because of last week's huge parties, Gaia, with its releasing of so many spectra, little spectra, but still spectra. SDSS-V is unique in that it is optical and infrared. It is 4π, just like Gaia, and it is multi-epoch, just like Gaia. And so for a ground-based facility to be complementary, and it's highly complementary to Gaia, partly because of this red piece here, that is the infrared high-resolution spectroscopy, or medium resolution to some of the spectroscopists in this room. I think these are the key aspects of SDSS-V. Now, fundamentally, what are we trying to do with these different mappers? So in broad brush strokes, the Milky Way Mapper is doing the formation and evolution of the Milky Way as a cosmological system and its stars, and that's about 5 million stars. Our local volume mapper aims to try to understand how all galaxies and all of their stars form and evolve. That's about 10 million spectra, but it's IFU spectra in the Milky Way and nearby galaxies. So we're really trying to look at high resolutions, high spatial resolution physics to understand how energy is injected into the interstellar media of galaxies. And our black hole mapper is looking at the formation and evolution of black holes, big and small. And that's about 500,000 black holes. And so in terms of what the key overarching questions are, and the questions that really motivate me, if you look at my scientific profile, I kind of work on all sorts of, I'm kind of one of a small number of theoretical generalists in that I work on a lot of different areas. And in particular, the things I'm interested in is, for stars, what is their structure, order, and multiplicity in life and death? So in other words, so many aspects of star formation, of galaxy formation, of cosmology depend very sensitively on stellar populations. And we have a very good model that explains a lot of stellar evolution, but in critical aspects of stellar evolution, in particular at high mass, and in particular with multiplicity, we have real uncertainties. And uncertainties that actually have gotten to the point where we need observations to break certain theoretical degeneracies. And that's what we're trying to do in the Milky Way Mapper. Now, for black holes are really easy. 2 numbers, mass and spin. That's it, you're done, okay? But we actually would like the mass function and spin function of black holes, and we'd like to understand how they evolve over time. So how do black holes get their mass? How do they get their spins? What are the pre-existing conditions within the stars that lead to that? So we're interested in this both at the stellar mass end of the black hole spectrum, and also, of course, the supermassive end, where we think they're regulating galaxies. And of course, galaxies, and this is very close to my heart, how do they actually work in the context of lambda CDM? And not plausibly so, like in my simulation, it looks right, but actually what's happening in nature. And that's what our local volume mapper is aiming to solve. The project is organized. This is our org chart for the project. We've actually filled that position, which is great. You can see there's many, many, many people who contribute. And of course, I want to highlight Andrew and Connie here, who actually participate in the leadership of the program. SDSS has many different places where you can lead, and I think that's one of the great parts of the program, but it's a lot of work. So whenever you see you're using SDSS data and you see one of these people, please do thank them, because they put a lot of energy into making the survey not just usable for their own science, but for the whole world through the public data releases. So looking at the Milky Way Mapper science program, and this is a slide from Jennifer Johnson, who I think awesomely put this little picture. There's a sort of core programs in our Milky Way Mapper. We have a program called Galactic Genesis, which is basically getting ages for millions of stars. We have a very large program on white dwarfs and in the solar neighborhood, stars in the solar neighborhood. We have a very big program on young stars, and in particular, massive stars, young stellar objects, and convective core stars. And these are central projects within SDSS. So these are things that will 100% absolutely get done, or we will consider ourselves a total failure. Not totally. Then we have what she calls shell programs, which is, I mean, this is just so adorable. I love it. Where we're looking at RV variability, we're looking at exoplanet hosts, we're looking at compact binaries, dust, and red giant seismology. These programs will get done, but they're getting done not at the expense of those core programs. So first we do all the targeting for these things, then we do the targeting for these, and then there are envelope programs, and these envelope programs are basically open fiber programs. The facility that we're building, and I'm going to describe it in a minute, is so powerful that there's a lot of time left over after we do these core programs and shell programs. There's a lot of time left over to do more science, and that's what goes in our open fiber programs, and that is a program focused on the halo, on clusters, on the clouds. Of course, there's other spectra that we take. Spectroscopic ages, this has changed the way we are able to look at the Milky Way qualitatively. So it's, of course, a quantitative change, but it also, as a theorist, it completely changes how you approach the Milky Way as a useful probe of galaxy formation. And we owe this to seismology. The fact that we can get precise ages from core masses and then bootstrap those precise ages to spectroscopy allows us to then get ages not just for hundreds of thousands of stars or 75,000 stars, as this old figure from one of our survey scientists, Melissa Ness, shows. This shows age gradient within the Milky Way. This is in apogee. In the apogee survey, this is 75,000 stars, and you can see that there are indeed age gradients within the Milky Way. But this is just an appetizer to being able to take the Milky Way, assign ages to millions of stars, and then compare those ages as a function of distance, as a function of everything, to what we predict in our simulations. Now, why does that matter? Well, in our cosmological calculations, we have so many different elements of physics that are competing, some of which are better modeled than others. But one thing that is a very robust thing that we predict in these calculations is formation time. So we know for a certain star formation prescription when stars form and how old they are. That's a really robust piece of the calculation. So being able to have that contact point with reality through these ages is incredibly powerful and something that we are hoping to exploit in our galactic genesis program. And this is just showing a color magnitude diagram. I mean, this completely changes how we approach the Milky Way. But I just want to point out that the SDSS-V program really spans the entire color magnitude diagram in terms of what we're working on. Now, this morning in the group meeting, we had much more beautiful color magnitude diagrams, and I need to update this picture with all the recent Gaia work. But this is just to show you how rich the SDSS-V data will be, because you just have to imagine, hundreds of thousands of stars with spectroscopy across this whole diagram. And that's just a different scale of problem that you can work on with that kind of data. And we're aiming to do for stellar astrophysics and Milky Way astrophysics what SDSS previously did for cosmology, and bring it into its industrial age. Now, one of the things that we've done is, and I mentioned in these shell programs, RV variability. Binarity, we know, is such a critical, this room knows, this campus knows really, really well. I'm looking at you. Hi, Pablo. So many of you are working on the just critical role of binarity in stellar evolution. And one thing that we would like to do is really understand multiplicity, both in how it relates to gravitational wave progenitors, but also supernova, also regular stellar evolution, and all of the interesting physics there, all the way down to planetary hosts. And in order to do that, you need high precision RVs. And so what I'm showing here is just the limit that SDSS-V will get to. This is for a typical star. You're showing the companion mass here. So here is a low mass companion as a function of separation. And you can see down to really dinky masses by the standards of stars. we're able to probe binarity at very large separations. So this is, and just to compare, this is the Gaia. I think this is maybe DR1, and this is final Gaia limit. So we're able to probe down to a much different regime and a complementary regime to Gaia in terms of really establishing the empirical facts of multiplicity across this range. This is another figure from Jennifer Johnson, and you don't have to look at all of this, but I want you to look at this figure just to show the radial velocity precision here and how it increases with signal to noise. So down at very high signal to noise, of course, we get extremely high RV precision, but we're much better than previous data releases of SDSS. So we're really pushing the RV precision in order to make good on this promise of multiplicity. I'm not going to go over this too much, but if you have questions about this, Andrew is the person to ask about it. But just to say, we heard a little bit about this morning in terms of we already have a huge sample of OB-A stars that we got during the PLATE program, and now in the actual SDSS-V program, the number is closer to 1 million stars in these samples. And so this completely, this is so important to understanding how stars actually form. And just to give a sense of how we're doing in terms of metallicity as a function of signal to noise, these are the errors on the metallicity as a function of signal to noise, but also for different elements, for the alpha capture light elements and iron peak elements. And this is a figure from Andy Casey, but you can see that we're getting to really high precision, even at fairly low signal to noise in all of these different elements. So it just gives you a sense of how powerful the data set is if you're interested in chemical abundances. Now, I mentioned about black holes being very simple, and what they're, I think if you've been struggling with black holes for a while, you recognize that mass is such an important aspect of understanding different theories of black hole formation. Some black hole formation models just don't work at certain masses. So it's really hard to make 100 solar mass black hole at the end of stellar evolution, and it's really hard to make 10 to the 4 solar mass black hole if you want to capture stars in an accretion disk. So actually establishing the masses of these objects is very important. And so we have a few different ways that we're tackling this. One is through our reverberation mapping campaign. So reverberation mapping is echo mapping, looking at how the broad lines in the quasar spectra, these are these, H beta, H alpha, how they respond to changes in the near black hole continuum, and getting a light travel time and therefore a mass from those objects. We're going to be getting about 2,000 objects with really precise black hole masses across a broad range of redshifts, which will be completely, it's a factor of 10 improvement over the standard, and we're very excited about that because a lot of these questions of black hole regulation rely on those precise masses. We're also going to be looking at binarity, like I said before. So we have a program to look at compact binaries, and in particular, if you have a black hole companion, that's something that it's another way to measure mass. So we'll be trying to look at this at low masses as well, but in a more Keplerian traditional way. Another fascinating thing we can do with our black hole mapper is, quasars change. Of course, we know that they're variable. We've known this since they were discovered. But actually looking at the variability in the lines tells us how the circum-black hole environment is changing. And in particular, these lines are generated pretty close in. So they're telling you how the accretion disk structure and the line structure surrounding that black hole are changing. And what we've observed is that it's not just the continuum that's going up and down, but these lines aren't just getting stronger and weaker. In many cases, they're going away completely. So here's the Balmer jump, and this is just looking at the Balmer jump at different times. So you can see, that here it is in the bright state and in the dim state. You see completely different. And then looking at H beta in the dim state and the bright state, So the line is just completely different. So this is encoding changes in this physical structure. Now, whenever you see a picture like this, and this is for the students, whenever you see a picture that has like a donut and some dots around it, that's an opportunity. That's an opportunity to make progress, because that means that we don't really know exactly what's going on. And so I want you to look at that and think about how you might contribute to improving this cartoon. And whenever someone talks about a cartoon, what they mean is we don't actually understand in detail how it works, and we need theoretical help. Just looking at the footprint of our targets, these are our eRosita. This is our eRosita targeting from the German eRosita sky. They actually were able to get to the depth for our targeting before they turned the mission off. And eRosita is just getting incredibly beautiful data. It's a beautiful mission, and let's hope that we can get this sky united sometime in our future. Our reverberation mapping and changing look quasar program is primarily in the northern hemisphere. So you see these blue dots are our reverberation mapping fields, and our changing look quasars, that is our multi-epoch quasar spectra, are there in the pink. There's also just cool stuff. I mean, when you see millions and millions of objects, you're going to see weird things. And so this is a page that was, this is from Scott Anderson, who's the Black Hole Mapper program head. There's now a remarkable objects page on our wiki, which just has really weird black hole spectra. So, so that's something to be excited about and to look out for. Finally, our local volume mapper. And this is really the theme. I used to work on cosmological hydrodynamic simulations, like for my day job, and one of the things that always frustrated me was that we got to this point where our calculations were degenerate. I don't mean that the calculation, like we were degenerates, but I mean that the calculations were not falsifiable with the data at hand. So we had beautiful mass functions, and every simulation group can predict a beautiful galaxy mass function with the right correlation function, and cosmologically it all looks absolutely perfect, precision, and then they would have very different physics under the hood. And if you care about physics and you care about the real world, not just the movies, then that's not really an acceptable state of affairs. So how do we solve this problem? Well, we have to go to where the energy is being injected, and we have to look at the physical conditions of the gas and compare it with our calculations to see if we're getting it right. And now, you know, part of what we have to do is look at many different galaxies, but we also can use the Milky Way and the star formation regions in the Milky Way and nearby galaxies to look at individual H2 regions. This is just a picture of Orion to give you a sense of how this works. That's an image. Here I'm showing stars that would be targeted by apogee, for example, in Orion. So this is the stellar input. You know, you'll have ages, you have ionization rates, you have metallicities, you have all sorts of all sorts of parameters from those stars. And then with the local volume mapper, we're doing an integral field unit spectrograph that is contiguous spectroscopy across this whole region. Every pixel here is not a fuzzy image, that's a spectrum. That's an optical spectrum at resolution of around 5,000. I gotta be honest with you, this is a lot of data. This is a scary amount of data. And just to show you why we need to go to that resolution, so if you wanna understand how stars are returning energy into the interstellar medium, previous observations look kinda like this. Okay, we got some stuff, and it's kind of fuzzy. So this is the, this is the kind of resolution of that H2 region. And so with the local volume mapper, we're going to this regime here, where you're actually resolving those structures So we talk about stars breaking out of birth clouds in cosmological simulations, and then we get the whole mass function. Well, I mean, is any of that right? I mean, some of it's right. We want to test it. We want to test it at this scale. So it's all about testing these predictions, not being satisfied that the predictions are just right. Just to show you what we're looking at, these are the dots here are our background fields. So it's all of those fields. It's the Magellanic Clouds and a huge swath of the Milky Way. This is just in our southern component. If we want to go north, which we ultimately do, we want to show success in the south, and then we need to raise more money because it's expensive to build this thing. So now to go to some of the hardware and why it's been challenging to do this, and particularly during the pandemic. I'm talking about ridiculous numbers of stars, hundreds of thousands, millions, blah, blah, blah. How is that happening? How is that happening? So the SDSS technology used to be these plug plates. So somebody used to plug a fiber into a plate every night. That would happen 8 times. And it would take 20 minutes just to change the fiber. And so what we've done in SDSS-V is build a robotic focal plane so that instead of having to plug the fiber, you just move the fiber. You just do it in software. The hardware on the program, the legacy hardware, we have 2 BOSS spectrographs. We have the Manga IFU system. We had an apogee spectrograph. This was all on our SDSS North telescope. And our southern telescope, we only had an infrared spectrograph. So this was our sort of legacy hardware, and of course it's the gold standard in ground-based data delivery for astronomy. People really, something that the students might not be aware of is that it wasn't always the case that we had data releases like the kind from Gaia. And SDSS played an incredible role in making that the standard. New hardware that we're building, oh my God. So we had to actually change this telescope because the way the corrector lens worked, you couldn't actually get a fiber robot to properly capture the light. The focal plane was not telecentric, and you need the chief ray to be perpendicular in order to use these robots. So we had to actually change the spectroscopic corrector lens on the telescope. We had to make 2 robotic fiber positioning systems. We had to upgrade the BOSS and apogee spectrographs with new slit heads and improved electronics. We wanted to get that RV that I showed you earlier, so we had to actually change the apogee spectrographs as well. So this was a lot of hardware. And we also had to build this LVM facility to do galaxy formation. So the LVM is a new observing facility. There's 3 spectrographs in each site. They're fed by 4 custom telescopes, and we had to build a whole new enclosure. So already, this is a lot of hardware to build, and this is like a crazy amount of hardware to build. So I keep on asking myself why they let me do it, because it's really insane in retrospect. But also, we did it, so I guess it was a good idea. But we didn't plan for COVID. So COVID hit us hard, as it hit everyone hard, and it first hit our colleagues in China. And so the first thing we did was say, oh, our colleagues in China they're locked at home for some reason. Maybe we should change our telecons so that they can join the telecons more. Not realizing, of course, that we were all going to be locked at home, and that our world was going to be totally different. Another thing we didn't appreciate is that when you have a pandemic, all of your contracts for building stuff are basically null and void. The companies, they don't have to actually deliver anything that you paid for at all. So it becomes really challenging to figure out, okay, like what can we build? Companies are literally going bankrupt as you're building. And then of course, the whole point of SDSS is to have universities build across this global consortium. So it relies on communication and coordination between all of these different places in order to build this hardware. So people had to accept deliveries in their garages because their labs were closed. So that's kind of how it's felt. I would say this is how I feel. Like I don't smoke, but anyway, it's been exhausting. It's been, and I said earlier, that's why I call these talks a bit of the coal mine, but I can say that we're turning into the gold mine. And so I want to say a little bit about the evolution. So this is a few of us in New York trying to figure out what we were going to do. This is a hilarious picture of David Hogg and our project scientist Hans-Walter Rix. And just goes to show that at the beginning, you really don't know how all this is going to go. And it really takes a lot of sustained effort and a lot of comfort in the vacuum. So you got to be able to embrace that uncertainty of the future. And of course, this is us commissioning in December. This is the first spectra from the Apogee spectrograph coming down the pipeline. And I took that photo. I wanted to be there for that activity. This is a bunch of us sitting around a table, once we kind of got the program going. And this is from 2018, or maybe late 2017, actually. And you can see the coal mine situation where so much zoom later, but it's actually working. You start with all of these pictures of beautiful pictures where all the hardware is like green and purple and pink, and like it looks so cool, right, in these CAD drawings, because you have to make things different colors in order to see it. And then you're like, oh, like, so what's happening? And of course, this is our Johns Hopkins team who built our SDSS, our new corrector. The telescope now delivers the best images that it has ever delivered. So it's time to put an imaging camera, and particularly in the infrared. So the infrared throughput of SDSS has gone up by a significant amount, tens of %. So how it started, again, with these colorful pink and purple images. This is a picture that our systems engineer, she was locked at home and wanted to understand, the systems engineer has to make sure that things connect. That's their point, like to make sure that, the person that's working on, the fibers actually knows where the holes are, because the person working on this part maybe didn't update their drawing or something like that. So our lead systems engineer actually built a cardboard version of our whole system, including wiring, to test out the routing. Now, normally you would just go and check all of this stuff in the lab, but that wasn't possible, so she built it out of cardboard. And then, of course, this is the actual system backlit here, and this is a picture of Rick Poggi, the program head, with Connor Sayers and Jose Sanchez Gallego. These two individuals actually are responsible for actually being able to acquire targets. They are absolutely critical. They are in charge of our control and operations software team and are just incredible. So we were so excited just to be able to figure out how these things work. So doing a crowded plane, most robot positioner systems have a zonal non-overlapping zones. So your robot kind of moves in, this robot moves in this spot, and the neighboring robot moves in its spot, and it's like, they're good neighbors, they stay away from each other. Our robots are all in each other's business, and so our robots overlap their zones, which means that they can collide with one another and get into fights, which they did. And when they get into fights, they pull the fibers out and break each other, so they can never collide. Otherwise, you lose a robot. So we want to have a peaceful, in general, we are for peace, and particularly in our robotic focal plane. And so you can see here how the algorithm that Connor Sayers developed to actually get those robots from one configuration to another configuration. And you can actually do this entire focal plane can be reconfigured in under 3 minutes, which is incredible. So compare that to the 20 minutes, but not just 20 minutes, because all of those plates had to be pre-drilled. So it's months. So we've sped up the survey from months to minutes. This is the previous sort of targeting cadence. This is from Apogee, and you can see the pattern. You can see the Kepler field there. You can see the pattern of plates. And this is where we're going. This is our projected target density in the Milky Way Mapper. So you can just see how transformative the program is. We are on Sky. The robots are currently taking data. This is a white dwarf spectrum here, and this is a quasar spectrum here. And you can see this is from Apogee, I think, and this is from, these are both from BOSS, our optical spectrographs. But we are on Sky and taking data, and it's so good to be able to say that to you here. And discoveries are being made. So this is a 99-minute double-lined white dwarf binary that was discovered in SDSS-V. So again, binaries, white dwarfs, critical. You're able to actually see the extra broadening of the lines from the time domain data in SDSS-V. And this is work by Vedant Chandra, and it was the first science paper in SDSS-V, so we're really proud of it. And you can see that this is a future LISA source. So identifying all of these sources is critical. Where are we doing with that? With the IFU survey? So that's just the robots. With the IFUs in 2020, this is kind of where it was. Again, look at all this: green, cyan, purple, red. They look so pretty in CAD. They look prettier in metal, actually. This is where we are. So now we have. Actually, this is Tom Herbst, who's building the telescope system. These are the these spectrographs are now, we have 4 of them at Carnegie, and Pavan Bilgi has been working to characterize them under Nick Konodaris' supervision. We have a lot of hardware that's been built. This is an enclosure picture. This is actually from May. Actually, now we actually have the structure over it. Which is pretty exciting. So you can see we have so much stuff that this is me with all of these crates in Carnegie a few months ago. These are spectrograph crates, and now there's even more spectrographs. So we actually have more spectrographs just coming than we can store. So that's pretty exciting. And now I think it's important to pause and realize we can build these machines to collect data, as hard as it is to build them, and it's hard. You can build them faster than you can understand all of the data coming from them. And this is where my Director Jekyll and Director Hyde come out. And I'll leave it to you to decide which is which. We need more calculations for all of these spectra. We need more simulations of black hole accretion disks. We need more calculations of the kind that you guys are doing in terms of binary stars and in terms of the interiors of stars, rotation rates, mixing, metallicity, pollution. We are definitely theory limited in a lot of these cases. And I love that because it is a great time to be thinking about these different data and testing these different models. But we are in desperate need for those calculations. So I think with that, on that note, I will end my talk and just say, we need you. We need your brains. Not that I'm a zombie, but I want your brains. Thank you.
Okay, thank you. Thank you very much for a super interesting talk. Are there any questions or comments? I'll come with the micro if you want. Well, it's super clear. I suspected that you would have a question.
Hi, very nice talk, thank you. I was wondering if your black hole part of the mission, you said you would cover like small masses and then the supermassive black holes. Like the stellar mass black holes, well, that's what I understood with the small masses, right?
Yeah. Yes.
I was wondering if you had like candidates that you specifically targeted, or whether you just have like, you observe all the sky and then you go like, these are the
So
ones.
what we have, and let's see. So this is the key, right? The key, well, there's two keys. So one key is the RV variability will give us some easy black hole candidates. So that's one thing at all these different separations, right? So that's one way. The other thing is that we're targeting Rosetta objects. And so the X-ray binaries are also potentially in the sample. And so those objects can also be spectroscopically observed, and they can be observed at multiple cadences. So there's sort of a few different ways to get at that stellar black hole binary. I think this way is the kind of just the raw statistical power of the program. But also the more specific, I fully anticipate that that's going to be very fruitful, looking at the spectra of those X-ray binary systems. Because there's like a weird thing going on, right? Why do X-ray binary spins look maybe different than the spins of gravitational wave sources, right? Like, why is that not, or is that really, do we really understand those two? Are they the same populations? Are we sure we understand that? And I think we, hopefully would at least be able to get some of the orbital information to start addressing the questions like that.
Okay, thank you.
Any more questions?
But will you get the spins as well?
Spins are so hard. We won't have spins from the spectra, right? So the spectra themselves won't. We're not looking at. Typically you're getting spins from the iron K alpha line, those kinds of things, right? In the X-ray case, and we don't have access to that. In principle, one can obtain that information, but SDSS doesn't give. We only do half of the problem, I would say. But I think in terms of, I think even if you specify the mass, and there's an important sort of, it's not like you can have any spins at any masses. So I think that's an important piece to constrain. But no, we do not. From the data, if all other missions were gone and all you had was the SDSS spectra on an island, you'd be busy forever. But you'd have to come up with some new way to probe spins, because we don't directly probe that in the spectra. I mean, there could be some interesting. It's good to think about, this is where we need more calculations, whether something in that multi-epoch quasar spectroscopy. But again, that's higher masses, so there's something to think about there in terms of how that spin would manifest in these other lines without actually broadening the line directly, right? But you don't have that direct probe.
Mm-hmm. When you say you need more calculations, you mean, I guess, simulations with more physics input?
Yeah, I think, you need really good radiative MHD accretion disk calculations that you can actually do the radiation transport and actually get the spectra as a prediction.
Relativistic right? Ones.
Yeah, I mean, so that is something, and people are doing them. That's not but the focus. There's been a really strong focus on doing those calculations for things like EHT, for example, and right. And now I think, having a data set that is a target for testing, I think is going to be, I'm hoping, a real motivator.
Right. So you gave a nice overview of your science goals, more sort of towards the astrophysics side.
Yeah.
I was wondering whether there are other sort of purely cosmological science goals in your program?
Yeah, so there's a few. The galactic so when I talk about getting these ages, right? That is, it's still galaxy formation, but it's really cosmologically motivated in the sense that we do need to understand this galaxy halo connection in order to, I think, more profitably make use of the large-scale structure surveys. And so I think both the local volume mapper, which is aiming to really understand feedback, and the Galactic Genesis program will address that. So Galactic Genesis gives you this galactic archaeology, and also there's morphological things. If the current dark matter, lambda CDM picture is correct, we should see all of this substructure in the phase space of the Milky Way. We do see streams, right? We do see dwarf galaxies, but we're not yet at the point where we're actually doing that cosmological experiment in the spectra. And that's something that we want to see with things with SDSS-V, probably in concert with things like DESI and PFS. But I do think the more kind of fundamental physics aspect that hasn't been really exploited, that I would like to exploit, has to do with making predictions, making predictions for those chemical, like nuclear physics predictions in the infrared, where we have the signal to noise to see new lines, basically. So there's some kind of basic nuclear physics that we should be able to do. But in terms of cosmology, like in terms of large-scale structure, those have all moved to bigger telescopes. And the thing that I'm excited about, if you look at SDSS-V, we're solving a lot of galaxy formation, galaxy physics, astrophysics, stellar astrophysics questions. But this is in the Mega Mapper, we really want to probe large-scale structure at the next level, right? So right now, SDSS kind of went from basically 2000 to 2020 and kept us on this line. We expect DESI to keep us going, through there. And the Mega Mapper is a new facility that would basically go 10x over DESI. This would be a Magellan-like facility with, I mentioned we made 6 DESI spectrographs. This is 32 DESI spectrographs. There's actually 10 in DESI plus 6 of SDSS, so we actually could do this. I showed you our focal plane. Our focal plane has 500 robots, right? Each robot carries 3 fibers, right? So 1,500 fibers. This is 20,000 fibers. So it's like next level industrialization. You would think that after the last 2 years, I would just say, no, we're not doing that. But in fact, it's so cool. Like, how could you not do it? Like, how could you not do it? And there's really interesting physics that can be probed with the Mega Mapper. So I'm not going to go into this, but basically primordial non-Gaussianity and all of those kinds of questions. But a lot of those large-scale questions actually do require kind of this type of scale of facility. So with SDSS, where we can make the most progress is in really pinning down a lot of this uncertain astrophysics that actually ends up being critical for things like galaxy formation, mapping the galaxies to their halos, understanding if this lambda CDM sort of halo that's roiled with substructure, if that's real. So I view this as everything but the equation of state of the universe.
Any more questions or comments?
Hey, Juna, thanks for the nice talk. I wanted to comment a bit on the black hole part and the spins, particularly the stellar mass ones.
Yeah.
In that from spectroscopy, you might end up finding a lot of black holes that are in very wide orbits, where you wouldn't expect nothing from an accretion disk to help you get information on the spin. Yeah. So it's a bit challenging how you
spins. I would never get up here and say that, oh yeah, we're going to give you spins. I think that there'll be certain contexts where we might be able to do something clever to get it, but honestly, the most robust spins are from the gravity wave sources.
Yeah, but just saying, a lot of these potential sources you would find might not have at all any counterpart from Eurosita.
No, absolutely, right. I mean, I think I completely agree with you there. Where I do think that we get at the other, so I view this as a boundary value problem, and where we get at it, right, is on the right side of the equation, we get at the masses. But on the left-hand side of the equation, we get in concert with things like astroseismology, right? We get at, okay, we've got this binary parameter, we have this spectroscopic setup. We know that there's some radial distribution of velocities, right? Then we put, theoretically, we kind of connect those dots. So I think that we are going to be able to establish some basic empirical constraints on the right-hand side. And theoretically, as you well know, that will constrain the masses and spins that we can plausibly get at the end of, the big, supernova shebang. And so I think that's the place where SDSS-V, feeds into the question of spins at the stellar mass end, not on the directly measuring spins, but on constraining those progenitor scenarios.
Yeah. One quick question is, just from colleagues, I always hear that they think SDSS-V is not that good for more or less the upper end of the main sequence, like quite massive stars. That it could be challenging to measure RVs, for instance, depending on the spectral lines you have available. So I don't know, how good do you think it is for O stars, 20, 30 solar mass stars?
So for for super high mass stars, right, everything is harder, and we do not yet have a high resolution optical spectrograph, and so that would obviously be better. But I don't think that we have exploited everything in the H band. So I actually think that we probably will end up doing a little bit better there. But as you know, once you get to, if you want me to tell you what the RVs in Wolf-Rayette's are, well, that's going to be pretty hard. But that's hard no matter what, right? So I think it really depends. I do think that, I do think that that we will have something to say up there, because once you're using the statistical power of the data, you can even use, with machine learning techniques, right? You could actually use high resolution spectroscopy on a subset to train, to bootstrap all the others, and we are going to have all of that data in the optical at low resolution or low resolution, depending on where you come from. R of 5,000 and R of 20,000 for those stars. But I definitely think that so we'll have information across the entire HR diagram. But if you're really interested in Wolf-Rayette winds, for example, which you might very well be, as you know, that's going to be a challenging observation, and I actually think we don't know how much we can do at that end yet, because we do have really high RV precision, and with multi-epoch you can untangle a lot of complicated astrophysics. So I wouldn't give up, but you can't look at it the way you're looking at your VLT program. It's a different type of experiment that you're doing when you're looking at, 1 million stars compared to one object that you want to understand precisely. And so I think you have to change mindset a little bit. But I don't know if Andrew, our survey scientist on massive stars, wants to comment further.
Well, on the RV precision, so from optical spectroscopy, we do get the RV uncertainties of 5 to 7 kilometers per second. Yeah, so we get there, and it's pretty good, I would say. But the problem is the number of epochs. So we get 3 epochs for these stars only. So for some discoveries, yes, but then we have to organize follow-up if you want to get orbits.
At least it gives you. At least 3 epochs gives you a minimum RV variation that's already giving you a minimum mass function. So I think that's quite good to begin with, to catch candidates, essentially.
Any more questions? I have actually one myself. It's a non-scientific one, actually. So every SDSS is more ambitious than the previous SDSS. And I guess also the cost price goes up. So if you take from 1, 2, 3, 4, 5, and you correct for inflation, is it a power law, or does it go
No, actually the
exponential?
cost, probably the first SDSS is the most expensive, and even corrected for inflation. But our cost is, in actual dollars, is the same as SDSS-4. So actually, and part of that is that SDSS it's built, frankly, with a lot of love. People stay up all night to work on the project. It's not like a 9 to 5 where you come in, do your thing, and like later we have a lot of people who are obsessed with figuring these things out, and that is impossible to cost. And I think that's why it's kept. It's been ambitious, but it's also kept in this mid-scale. And we really hold ourselves to a standard of if we can't make an ambitious and exciting program, using innovative technologies and, our hearts and minds, then we can't continue. And so that's a very scary thing in between the transitions. So we're not funded at the beginning, and Connie can speak to this. It's a very, and everyone's like, well, you're just going to give away the data anyway. And you're like, yeah, that's true. But we can't get the data if we don't get funded, so we're in a bit of a catch-22. But I would say that spiritually, SDSS is a very different type of program. It's not, it's not meant to be. It always will stay in the mid-scale because that's all you can do under this model, and hopefully we'll always be pushing that innovative boundary so that, in particular, young instrument builders can get their hands dirty, figuring out how to make instruments work, figuring out how to characterizing them, like staying close to the data. I think that SDSS does fill that role, that critical role between, going to the telescope with your advisor and taking, your very precise, Wolf-Rayet data, and getting data from, spacecraft, and so I think there's a lot of that we just have a lot of zealots. It's a religion. No, it's not a religion. Bleep that out. It's not a religion. It's science. It's our inalienable right.
Okay. If there are no further questions, thanks Juna again. Thank you very much.
Thank you.
Email you this. It's a little known manuscript.
Okay.
The archives of the Mapper.
Oh, really?
From 1958. So late in his
please,
life.
please do.
So I just checked it in English, and so this sort of a manuscript on structure formula.
Yeah.
So not on the expansion.
Okay, on actual structure. Okay.
Yeah. So in the 50s he worked on structure formula. That's the first sentence. The problem of structure cannot be separated.
Oh my God.
Wait.
It looks like it said from cosmology.
Completely from cosmology, yeah.
Oh my gosh, can you please send that to me? That's amazing. That's amazing.
Yeah, it's kind of, he really got hooked up this...
that guy.
Yeah.
Oh my gosh.
In the 1930s he had this super toy model, a la Schwarzschild, essentially, which he used locally for stuff.